So the advance itself is very technical. It's very artisanal. It took a lot of hands-on trial and error for my students to figure out what are the right conditions to get this to work. But now that we have it working, we've now essentially shined a floodlight on this area of exploration that was previously completely dark.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
Joining me today in the ASC Marketing and Communications Studio is Ezekiel Johnston-Halperin, Professor of Physics at The Ohio State University College of the Arts and Sciences. His experimental research program includes fundamental questions of condensed matter physics, the discovery and synthesis of new materials, and quantum information science and engineering, with an emphasis on spin and magnetically active materials and phenomena. Dr. Johnston-Halperin, welcome to Voices.
Thank you for having me.
Well, and I wanted to start maybe with a definition of quantum information science, which I'd never heard of before. What is QISE?
Yeah, that's a great place to start. The right way to get going is to just break it down.
Like a physicist.
Scientists tend to be painfully literal in our acronyms, so there's some guidance there. And so let's just focus on the quantum and the information. So the quantum piece comes out of this centuries-long history of quantum mechanics. There's a lot to unpack there, obviously, and we can circle back. But so that sort of labels the branch of physics that it's involved in. And the information piece actually, I think, is most helpful if you think of it in terms of the modern concept of information technology. And so the consumer-facing pieces are computing. Everybody knows about that for IT. Networking, since the 80s and 90s. A little less consumer-facing, but really still important from a technology standpoint, is sensing. And so one of the leading areas of computer science, if you will, information technology, is what they call edge computing, networked sensors, arrays.
So when you say edge computing, give us a little sense of what that is.
So, and again, here, this is the edge of my expertise. So apologies to my colleagues in the area if I get this a little bit fuzzy. But if you imagine the internet a la 2000, 2010, it's a bunch of computers plugged together in a web of connection. And then as you move forward, those computers are individually talking to local sensors, microphones, speakers, but also in your car, there's an accelerometer, there's GPS. So those sensors, if you lay that out as a map, there's the edge of the map where all this kind of like the endpoint interface between the information technology and the physical world exists. So that edge computing is a very active area of development right now. Sort of a classic scientist academic move here is we have an emerging field, so all of a sudden everything else becomes classical. Classical computing as opposed to quantum computing. But so it's, I think, a really helpful place to get started because quantum mechanics writ large affects literally everything in STEM.
So maybe we should start with a definition of quantum mechanics. Sort of remind us, as you say, this centuries-long scientific movement. Tell us what quantum mechanics is.
So this is the language or the model to describe, if you like that language better, how the elementary particles behave. Here we're talking about electrons, protons, atoms, neutrons, particles that you'd find at CERN, like the top quark, basically the fundamental building blocks of the universe. How do they behave? Light is actually one of the through lines here. Our understanding of how light behaves is one of the key drivers of our understanding of quantum mechanics. So the quantum mechanical revolution, which included people like Niels Bohr and Einstein and Heisenberg at the turn of the century, really fundamentally reshaped everything we know about science: biology, chemistry, physics, engineering of all sorts. It all traces back, has some impact on quantum mechanics. So the quantum information revolution that's happening now is broad, but not quite that broad. It's not everything about quantum mechanics, but it's an aspect, an offshoot of quantum mechanics that can be harnessed for particular impact in information technology, in computing, networking, sensing.
You are working in particular in the area of magnetism. So I want to talk first of all about your work in this area.
Okay, so I'm going to take a big step back from quantum information to do that because interest in magnets is older, and my professional interest in magnetism and what makes them work predates this quantum information piece. And one of the things that I like to point out to new students in the area is that there is no classical theory that explains how magnetic materials work. So electromagnets, Maxwell's equations, which people may have had if they had a freshman physics class in college, that you can do sort of classically. But what makes a chunk of iron magnetic, which goes back to lodestones 2,000 years ago for finding direction, there just is no way to explain what makes a chunk of iron magnetic without quantum mechanical descriptions. So it's literally this miracle that is with us every day. And this is part of what I love about science is it's really this double-edged sword where it feels like such a pedestrian miracle to us. Because as a kid, you grow up, you play with magnetic toys, your parents put your fingerprints up on the fridge. It's just a magnet, it just works.
I just assumed that this was a problem that had been solved.
Right, because things that we onboard that early in our development, you just kind of get okay with it. That's just how things go. But it's really not. It's really a fundamentally quantum mechanical process. And so the opportunity for learning new things about how nature works by studying magnetic systems is really kind of profound because it's cutting edge quantum mechanics, yet everyday phenomena. I mean, we're pushing it to new regimes. We're not studying only the everyday effects in 2024, but you can get a start in just sort of the everyday approach.
So what sorts of things are we learning, or what sorts of things are you learning about magnets and magnetism?
So one of the things that I really enjoy about the practice of academic science is it's a very flexible enterprise. How that works well with my personality is over time I've cultivated what I like to call constructive laziness. So I want to do fun things, but I want to do them as easily as possible. And so with a discipline that's very flexible, that means I can tune the way I do science to play to my strengths, things I'm good at, things I like to do. And in the study of magnetism, there's questions that go all the way to the fundamentals of how magnetism works. And again, a famous problem in physics is you have individual electrical charge on electrons, and Maxwell's equations has a symmetry that says, okay, there should be then an individual magnetic charge, but there's not. Our universe says magnetism only comes in pairs, only in north-south dipoles.
Right.
That's a profound question about how our universe is structured. All the way up to how do I make, safety devices for industrial machinery that are based on magnets and magnetic memory for computers, very practical applications and everything in between. So in my research group, to the extent that we can, we enjoy sort of climbing up and down that ladder within a given project. So some projects start off with a fundamental insight and we look for the implications up that chain of development. And then others, we start with a question and we start poking, like, we'd like to be able to do this. Say, currently, problems in quantum information. What's a good way to get two quantum states to talk to each other so the information goes forward but not backward? How might we do that? So there's lots of different ways to be successful in science, and that's one of the things I love about it. But that's the way that I think my research group tends to function is basic questions of materials. What makes a magnet, different ways to measure, like how can we measure a magnet? Like we can construct in our head a cartoon of what we think is happening. Great. So far we're philosophers, but we want to also be natural scientists and like what can we do in the lab that can test whether that's actually what's happening? And then, as I said, on towards applications and seeing if there are fun things that we can use this to help develop technology.
Why magnets? Why magnetism? What drew you to that question of all the questions a physicist can ask?
That's a great question. And let me start a little bit high level as I have been talking, but then I'll get real concrete. So I think something that's often missed about science is the human aspect of it, because ultimately it's a quantitative, concrete enterprise. But those questions about why study this and not that are fundamentally human. They have to do with like my personal interests, our collective interests, and what we choose to support and fund as a society through federal science agencies. So big picture, why magnets is because personally I have a sweet spot of what I would call the complexity of the problem, where I like to operate, which is to say messy, but not too messy. So, and traditionally in physics, I tend to be much more towards the messy side. A classical physics approach is to say, well, I want to understand how atoms work. Get me a hydrogen atom. One proton,
Yes.
one electron, I'll work on that.
The simplest atom. Yes.
Exactly. All those other atoms are a little too messy for me. At the other end of that spectrum, I consider, for example, life sciences, where we have some collaborations and really exciting, important questions, but the systems are so messy that it's very hard to get to first principles, which doesn't make the science any less fundamental. It just leads to a different style of problem solving. So in this sort of intermediate messy zone, the style of problem solving that's most important is looking at a very complicated, confusing set of phenomena and trying to find the thread that connects them, that can bring some order to that chaos. And that, I think, is the type of problem solving that I'm just sort of naturally drawn to. So why is magnetism messy? Then like what makes it this? So here, I'll start with what sounds like a metaphor, but actually has very foundational physical alignment. And so coming back to my earlier statement, that we're only okay with magnets being spooky because we grew up with them, right? So another phenomena that's spooky that way and has maybe even more tactile impact is how to ride a bike, right? It's a famous aphorism, right? Everybody remembers when they learned how to ride a bike.
Oh, yes.
And it's not a super intuitive process, right? There's a reason 3-year-olds don't ride bikes. You got to, 5, 7, whatever. It takes a little while. And if you go to a freshman physics mechanics class and you wait till the end of the semester, they've learned all the mechanics that we're going to teach them, and we ask them, why doesn't a bike fall over? That's not a question we would ask freshmen. In fact, that's a pretty challenging question for seniors.
You would not ask that of freshmen.
No.
It seems like a simple question, but maybe it isn't.
Well, no, and this is the essence of science in the sense is not all the questions that are easy to ask are easy to answer. And we do have, obviously, answers. We know how bicycles work. And, I don't want to get too deep into the weeds here, but I'll say briefly that this has to do with the rolling motion of the wheel. This creates a property of any rotating object that we call angular momentum. And this sort of describes how an object is rotating, how fast it's rotating. And for a bike tire, it has something to do with how heavy is the tire, how massive is the object that's rotating. And it turns out that the way forces act on a rotating object is different than the way they act on an object that's just sliding or translating. So one analogy is you can imagine the pendulum of a grandfather clock. Mm-hmm. So it starts at rest, and I push it to the left with my finger and I let go. That pendulum is going to smoothly translate back to equilibrium, right? Its motion is going to come back in the direction that I pushed it. So if I push to the left, it'll swing back to the right. If I take a bicycle tire and I push on the axle forward, so now I'm rotating the tire, sort of like turning the handlebars, it doesn't push straight back, it tips over. So like if you fast forward into like motocross or something like that, you can see them leaning into the curves. This is that effect. So you push in one direction and you get a reaction 90 degrees. So that's odd. That's not the way our brains are sort of programmed to experience the world just through everyday living. So it takes some time and some study to understand that. So magnetism does exactly the same thing, and it turns out for exactly the same reason. So I said earlier that we can understand electromagnets with classical understanding. The short version of that is that if I take a loop of wire and I pass a current through it, where that current passes in a loop, it generates a magnetic field. So this is like how solenoid switches work, lots of everyday applications. And now I'm going to employ a sophisticated educational technique we like to use in physics that I like to call lying. So I'll briefly lie to you, but I'm telling you I'm going to do it, and I'll point at the lie. But it helps us get across the bridge and sort of skip some of the formal detail that's not important here. So if we imagine the electron as a ball of charge, it's a ball of negative charge, which is a lie. An electron's actually a point. It doesn't have size. But we just imagine it's a beach ball, and we paint negative charge everywhere. And then we start it spinning. And now I want to look just at the equator of that beach ball. I've got a ring of charges, and they're now rotating. If I squint my eyes a little bit, that looks like a current going in a loop, which generates a magnetic field. So there's a very fundamental relationship between this angular momentum, this rotation, and the presence of magnetism. And this gets even better. And this I'm absolutely not going to be able to explain on the fly, but I'll just point it out because it's one of my favorite things of physics, is if you take that understanding and then you follow the concept of relativity. And we'll just start with normal relativity, which basically means that if I do physics in Columbus and physics in Dayton, it should look the same. Basically, if I change my reference frame, physics should still work. We don't have to come up with different rules of physics in different places. So that's been a bedrock since, the Greeks.
The Greeks, yes.
When I say the word relativity, probably the first thing that people think of is actually special relativity,
Right.
which Einstein pioneered, again, around the same time that quantum mechanics was evolving. And that adds some additional rules, how physics has to change as you move place to place in order to keep physics functioning. And those rules only apply in relatively extreme circumstances when things are moving very fast. And so this is like the speed of light is a constant is famously where this comes from. So it turns out, though, that if you take the rules of quantum mechanics and you say those rules have to follow the laws of special relativity so that the rules of quantum mechanics look the same no matter where I'm looking, electrons have to rotate. They're always rotating. In the glue of the universe, electrons have this property of angular momentum. We know they have charge.
Right.
Therefore, they must have this little magnetic moment that we like to call spin. And so I'll probably revert to that terminology as we start talking more, because spin and magnetism are really interchangeable. So I know that was a really long road. Let me circle back. Why am I interested in magnetism? Because it's in this sweet spot of exciting and important, but not so intuitive, not so obvious what's going to happen. It's got just enough messiness to surprise me about what I'm going to find. And why is that? Well, it's basically the same reason why bikes, also gyroscopes, not just the toy gyroscopes, but the ones we put in airplanes and spaceships to keep them on track. That same physics is baked into the structure of the universe, and its manifestation is magnetism. That just leads to all kinds of fascinating little corners and quirks and surprises in science that I've spent most of my career exploring different avenues along those lines.
When you were a kid, did you know you were going to be a physicist? Or did that come later? And I guess the question is, why physics? Why are you a physicist?
It's an interesting question. And, I think my perspective on how to answer it obviously has changed with time. My elevator pitch answer when I was a college student or maybe a graduate student was job one at the top of the list was Luke Skywalker.
Of course.
As soon as I appreciated that that wasn't possible, physics was the next best option. Another way to say that is, as a child and still today, an avid fan of science fiction and fantasy, there's many reasons to enjoy works of art. For this conversation, I'll focus on the fact that I think at their best, those genres are the literature of ideas. And so they pose really interesting ideas and say, what if? And they're fascinating thought exercises. But once you start scratching the surface of science, you realize science often has a very dusty reputation. And there's reasons for that, and many of them are justified. It's maybe a separate conversation. But if you really start scratching the surface, you realize, no, we can do things that are every bit as cool as magic or warp drives or whatever you might find in your science fiction or fantasy book, but we can actually work on it and make it go. Individually, collectively, we can gain control over those systems and figure out how they work and try new things. And so I think that's the thread that sort of pulled me into science. Is like, I think, like many people of my generation, I'm solidly Gen X, science nerd. Of the time, I read A Brief History of Time by Stephen Hawking, and decidedly did not go into general relativity for my professional career. But I think, books like that are so valuable because it highlighted, here are ideas that sound every bit as exotic and exciting as anything I would read in Tolkien or Heinlein or whatever. But these are questions we actually have leverage on. We can go out and follow up on those ideas and see what's true and see what's not true and see what's even more exciting than what we started looking for in the first place.
Before we started recording, you had said something to the effect of, I'm also fascinated by questions of how things work from the perspective of human behavior, politics, literature, and art. Say a little more about what that means.
So I came within one or two classes of double majoring in history in college. I have a history minor.
No kidding. Well, you're preaching to the choir here.
Yeah,
So
an avid reader, as I mentioned, and for whatever reason, the questions of why that we've been talking about related to my research, at some level, it's inevitable for me. Like those are just the questions. That is how my brain is wired, for lack of a better way to say it. I'm just always curious about why. And so if we want to, go into the Marvel parallel universe kind of view of the world or something like that, if there are alternate worlds out there, in a sense, I could very easily have ended up asking those questions of why on many different subjects. When I was younger, it felt a lot more just fortune that I ended up in science as opposed to how governments form. How do you get groups of people to behave in a certain way? How does the culture of science work as well as the practice of science? So I don't know whether this is a me getting wiser or just me getting more entrenched, wiser about myself. At this point in my career, I see a certain inevitability, again, just very much though at a personal level, because I think, as I said earlier, the practice of science is very quantitative and concrete, but the decision about what questions to ask is ultimately personal and is sort of decided by, at least in my opinion, what answers do you find satisfying? For me, it's less what questions do I find interesting. They're all interesting. But if I'm thinking about my career, what's going to get me out of bed every day? What's going to keep me engaged and excited and showing up to work? It's less about the question and more about the answer. Where am I going to be able to put my energy that's going to generate answers that I personally find satisfying? And that's 100% a choice. Many friends and colleagues who are not particularly satisfied by the science answers, and they're much more focused on the more human-centric or political or whatever, which is great, also very important. That's just, like I said, that's not going to get me out of bed day after day after day, coming back and asking those questions.
You said one of those questions is why, and it's why I became a history major, because I was not going to be a history major till I took my first class, and on the very first day the professor said, history is a study of why, answers the question why, and I was hooked. So it's an interesting parallel there.
Yeah, absolutely. I mean, hard to imagine a more interesting question.
Exactly. Well, tell us your next why question. What's next for your research?
So thank you. And we're at a pretty exciting pivot point where for the last several years, my postdocs and graduate students have been working really hard to develop a new technique that'll allow us to start asking very interesting questions about new systems, specifically about molecular systems. And this is sort of a classic move in physics, is to see an area of darkness of where we don't understand what's happening and try and understand what new tool can I build that'll allow me to look into, Galileo's one of the famous ones, right? He literally built a telescope to look into the darkness. This is a little bit more metaphorical, but in the same spirit. And so throughout my career, and I think in science, there's sort of two parallel tracks in quantum mechanics and now in quantum information. So one is a very solid state view. You can think of this building through solid state electronics, the kinds of things, microelectronic circuits that Intel is building in new factories and solid state lasers and all kinds of really powerful technologies. On the other hand, if you ask the question, I want to really engineer individual quantum states. I want to take an electron and I want to treat it like taffy and pull on it and twist it. What are my tools for doing that? Well, that's actually chemistry. So you take an atom, you start attaching other atoms, they interact, they change their properties. So chemists have this great library for how to tune the properties of a quantum system. So historically, they haven't been asking about how do you tune it to make it a good quantum information system. Just as physicists haven't been asking, how do I make a transistor that's useful for quantum information? Because nobody realized that was an interesting question to ask until more recently. But both communities have really started asking this question, but those two endeavors are really separated by some significant technical barriers. And they're pretty prosaic. If I just say the word chemist to you, you might imagine someone in a lab coat with a fume hood and some boiling beakers, and they can do amazing things, right? And obviously that's a caricature. But then if I talk to you about microelectronics, you're imagining some Intel commercial from the 90s with people in funny suits dancing around. Just very different physical environments for those two systems. So we've been really thinking about how do we pull these two things together. And it turns out that we've just been able to demonstrate the ability to do this. We're submitting a paper for publication now, and we have a patent pending on this, which takes advantage of another revolution in science associated with 2D materials. So this actually led to the Nobel Prize a few years ago. I'm embarrassed to say I don't remember exactly, 5 to 10 years ago, in the discovery of graphene. Mm-hmm. And so this is basically taking graphite, the material and pencils, and it's literally as easy as sticking a piece of graphite between two pieces of Scotch tape, and then you just keep peeling, and the graphite fractures and sticks and fractures and sticks. And if you keep doing that, the way graphite is put together, it's essentially a loose stack of single sheets of carbon arranged in this hexagonal pattern. So if you keep peeling, you can get down to single atomic layers of carbon. This is amazing. It's a completely different approach to getting to the atomic scale than anything that we'd tried before. And there's been a whole explosion of people looking at these two-dimensional materials. 2D materials is sort of what the area is generally described as. My group had dipping our toe into this field. I have colleagues who are doing great work here. Very fortunate here at Ohio State to have a lot of people like Jay Gupta and Roland Kawakami and Jeannie Lau and Mark Bachroth in physics, Josh Goldberger in chemistry, and many others who I apologize for leaving them out. But, I got sort of a ringside seat to see the very exciting things they were doing here. So with apologies to all of them, our thought was, well, what if we do the most boring thing possible with those really exciting materials? I just want one sheet of atoms that's a conductor and another sheet of atoms that's an insulator. Sort of the very basic Ohm's law building blocks of making a circuit. But the trick is, because of this technique called exfoliation, sort of similar to the skincare routine, you can exfoliate out these flakes and then come in with basically a stamp that's just slightly adhesive and pick them up and stack them like you would stack a deck of cards. So you can atomic layer by atomic layer say, I want 2 layers of conductor, 3 layers of insulator, another layer of conductor, whatever you want. So our idea was to build an electronic device that's a conductor, a conducting layer, an insulating layer, and then a conducting layer. So it's just got 2 electrically conducting layers that come and meet in this insulator. And we can pass a very small current through that insulating layer. And that current then is very sensitive to any imperfections in the device. So we can design it so basically it just barely doesn't work. There's no current coming through. And then if you add any little defects, any dirt in the device, then the electrical charge can pass through that dirt. And in some sense, this is now a bad device, right? Because now it's leaking is the term of art. But what we realized that if we make the device very clean, we can then intentionally add in exactly the flavor of dirt that we want to study, if you'll allow me to extend the metaphor. And so what we can do is put down a layer of conductor, a layer of insulator, and then just evaporate a single layer of molecules on the surface, and then put more insulator on top, and then more conductor. So basically this molecule is trapped in between these 2 layers of insulator. That encapsulation protects the molecules from the environment. It allows us to electrically contact those molecules. And as we pass current through that device and study its properties, monitor that current under different conditions, then we can learn about the properties of those molecules. And in fact, the quantum mechanical properties of the quantum states that we have engineered, or our chemistry collaborators have engineered those molecules to have. So effectively what we've done is we've taken these molecules which lived in the test tube, and we've now developed a platform that allows us to integrate it into a solid state device that we can probe electrically, that's now completely compatible with all these other solid state quantum electronic devices that people are developing. So the advance itself is very technical. It's very artisanal. It took a lot of hands-on trial and error for my students to figure out what are the right conditions to get this to work. But now that we have it working, we've now essentially shined a floodlight on this area of exploration that was previously completely dark, completely, opaque. And we can start asking these questions about quantum mechanics and quantum information about molecular systems, use the tools of chemistry, or our collaborators. And to be clear, everything I'm talking about is a massive collaborative effort within my group, outside my group. So we can integrate these devices, these molecules into a solid state device, and we can take advantage of all of the atomic scale engineering that the toolbox of chemistry allows us to use to create custom quantum states that we can now integrate with the whole library of existing solid state electronics and quantum electronics. And so we're really excited about the potential for this direction. And so I mentioned there's lots of different applications of quantum information. We think the natural place to start with this type of quantum system is for quantum sensing. So these devices are very, very thin. They're, say, less than between 5 and 10 nanometers tall. And so that means that if we take other systems, other materials, and we bring them, basically put them down on top of this sensor, then the molecules, the quantum state of the molecules in our electrical device will be perturbed by whatever we put on top. So we can use this for like materials characterization, which is kind of a generic sounding business to business behind the scenes kind of thing, but really a very important piece of the economy. More potentially sort of obvious or easy to access directions are characterizing molecular structure, molecular dynamics, how molecules move. So if I have now some unknown molecular system and I want to understand how does it react to light, or what does its structure even look like, how does it behave in certain environments, we can essentially put it on top of one of these sensors and study it as it behaves. And, the holy grail for this kind of direction, and this is not an insight unique to our research program, this is something people are very, the whole community is very focused on our applications in like drug discovery, for example, is, one of the classes of molecule that you can study are potential pharmaceuticals, for example, and you could integrate them with this kind of quantum sensor and learn more about how those molecules behave. So that's a very long range vision. In the physics department, I often like to joke with my colleagues, we only do things that are useful by accident. This whole quantum information revolution was not to discount the foundational work of people who worked for decades to make this happen, but it's a bit of luck that it ends up actually being so important. And so that those kinds of applications are very much downstream. I don't want to overly feed the hype cycle, but that is one of the North Stars that's sort of leading our efforts. Why are we interested in these systems? Why are we asking these questions and trying to get these things to work?
Ezekiel Johnston-Halperin, thank you.
Thank you.
Voices of Excellence is produced and recorded at The Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Produced by Doug Dangler. I'm Jen Farmer.